Hello, welcome to Physical and Structural Geology. Why are we taking this course? We are taking it to introduce you to the basics of geology. What are the basics of geology? To study the composition, the structure, the processes, and the history of the earth. Okay? Composition, what makes up something. So with respect to geology, we want to find out what makes up the earth. The structure, what are the layerings in the earth? How does the earth look like from another perspective? Processes, what things go on or what things went on during the formation of the earth, and some of them are still going on now. History, what was the history of the earth? How did the earth come about? What are the things that went on during the formation of the earth? And what are some of the ideas of the formation or the generation or creation of the earth? This is the course outline. We'll talk about the general geology, then internal processes, geologic time, plate tectonics, weathering and soils, mass wasting, groundwater, streams and drainage, wind action and deserts, volcanism, and then an overview of geological structures. So as you remember, the course name is Physical and Structural Geology. So from chapters 1 to 10, we talk about the physical geology, and then the chapter 11 will talk about the structural geology. Moving to chapter 1, the general geology. So what is geology? Geology. Let's split the word into two. We would have geo and logy. Geo was taken from the Greek word which means earth. Okay? And then the logy from the Greek word logos, which means study. So geology is basically the study of the earth. Alright? Now into details. What is geology? Geology is the study of the earth, including the materials that it is made of, which is the composition. Materials that it is made of. Materials. Just a second. The materials that it is made of. That's the composition. The physical and chemical changes that occur on its surface and its interior. Alright, so this refers to what? The processes the earth goes through. And it is these processes that result in what? The structure of the earth as well. And then finally, the history of the planet and its life forms, which is the history. So geology is basically these four keywords with respect to the study of the earth. So if someone asks you what is geology, you can just say geology is the study of the earth with respect to its composition, structure, processes, and history. If you want to go into further details, then you state all of this. Alright, we are saying the Earth's radius is about 6,370 kilometers. The radius of the Earth. It means the diameter will be times 2 of this. And if we mention the word radius, it means the object itself is what? Circular. Alright, and so that's how come you are having a radius in there. So it's circular, and then you can measure the radius from this side to another side, giving you what? The radius. And you are seeing the radius is what? 6,370 kilometers. The rock outcrops form some of our planet's most spectacular scenery. White chalk cliffs, pink sandstone arcs. Alright, so we are saying that the earth is made up of rocks, and then these rocks are beautiful when you get to see some of them, like you can see on the right side of your screen. Alright, different shades. You can see the lower right bottom, black, white, cute. Then over here you see that there is some alignment. Okay, so these are alignment of mineral grains within the rock. Okay, you see another beautiful one here, different colorations of blue and lighter colors. Alright, white here. So rocks make up very beautiful scenery for the earth. Rocks in turn are composed of minerals. Okay, although more than 3,500 different minerals exist, we are saying that fewer than just a dozen are common. Okay, there are many minerals that exist, but then just a few of them are common. Geologists study the origins of the earth, the properties, and then the compositions of the components that make up the earth. Alright, so what are these components that make up the earth? One of them are what? The rocks, and then the minerals. Minerals make up rocks. Okay, so these are the basic foundations of what geologists study. Why is it necessary to study the earth? For curiosity. You want to find out why is it that when you drill a borehole, you are going down into the solid parts of the earth. How come you are getting water out of it? That is something that should make you curious, because you're expecting that, oh, the deeper you go, it should be more solid, and then it could even be hotter and all that. But there's water there. You are curious. What's going on there? Someone also is trying to find out the source of a stream or a river. It keeps going backward towards the upstream area, and realizes that the source of that stream or that river is what? From a rock. So all of the water coming out are coming from what? A rock. So curiosity, you want to study how come these things happen. What is the force that is driving some of these things going on around us? The other one is what? We are part of it. You are on the earth, so it's just nice to know some of the things that go on around you. You are in an area where there is an earthquake activity going on, and then you start to think that, oh, maybe the gods are angry with someone, or some ancestors are there. No, that is superstition. But then as a geologist, someone who has studied geology will know that, oh, this is certainly supposed to be an earthquake, and an earthquake occurs when there is some form of vibrations within the subsurface. Okay, because we are part of it, it's necessary to know the things that go on within the earth or on the earth. Why is it necessary to study about the earth? Because of the energy and the mineral resources we get from the earth. We are out here because of money, right? Miners, environmental guys, everyone. Money. And the money we get it from what? Mineral resources. We get it from what? Energy. And all of these things are found right within the earth or on the earth's surface. So it's necessary to study and know about the earth so that you can tap into these resources to make some wealth. Geological hazards. So we have tsunamis, we have floods, we have landslides. I mentioned earthquakes earlier. And all these activities, we should have an idea of them and to know what to do when some of these things occur, or sometimes what we should do to prevent their occurrence. Okay, and it has the same to do with environmental concerns as well. And then the earth materials and processes. It's nice to have an idea of the materials that make up the earth and the processes that go on within the earth and on the earth. Some of the practical aspects of geology are the use of natural resources. Okay, so natural resources, all manufactured objects depend on earth resources. Okay, so for instance, we are picking just this small pencil as an example. The part where we used to write is gotten from what? Graphite. Okay, then the portion which holds the graphite is made up of what? The clay, and then the other parts, maybe wood, they are all gotten from the earth. Alright, the paint, the iron that is used as part of the design, and all that, the machinery that are used, the copper and the zinc which make up the brass are used to hold the eraser. The eraser is made up of petroleum products. All of these are natural resources taken from the earth. Alright, it says if it can't be grown, it must be mined. If there is any resource that cannot be grown, maybe food, rice, maize and all that, they can be grown. These are resources that we know and we use. Okay, the ones that cannot be grown are the ones that can be what? Mined. So it's either you grow or you mine, and then the mining is what geologists normally leverage. Coal mining. We are saying in coal mining, careless mining can release acids into groundwater when there is some form of leakages, okay, and then the coal is released on the surface of the earth. It leaches into the earth and then it joins the groundwater, and that's where we get our borehole water from. When you drill and then you tap into such a groundwater resource, you are contaminating yourself. You are drinking polluted water, you are drinking acidic water. We also have petroleum resources. The removal of transportation as well as the waste disposal can also damage the environment, and this has to do with what? Environmental protection when it comes to extracting resources. So resources should be extracted carefully with so much caution to make sure that they do not pollute the environment or cause any damage to humans and the ecosystem. Dwindling resources can encourage disregard for ecological damage caused by extraction activities. Dwindling resources, you feel that, maybe in Takwa area or the western region or eastern region or central, you see that maybe the gold is getting depleted, so everyone is rushing to get their own share, and then along the line there is disregard for ecological damage. All the plants and all the other living organisms that live in the ecology, they are disregarded. Trees are felled, and then the river bodies are polluted, all in the process of what? Extracting activities. And this is what is going on here in Ghana. So much deforestation, so much pollution of our river bodies, and then we are suffering for it because people are rushing to take advantage of the dwindling resources, and they are doing that with disregard for ecological damage. But you, as an engineer, you will not be like that. Okay, and geological hazards. So we have earthquakes, we have volcanoes, we have landslides, floods, wave erosion. All these activities happen in nature, and they have direct influence on the earth and the inhabitants. Okay, shaking can cause what? Damage to buildings, and then break utility lines. Along the line, some of these leakages, maybe gas is leaking somewhere, electrical cables are somewhere. When there's a little spike of fire, it can result in fire outbreak, can result in destruction of other properties that may even eventually lead to injuries of humans and then loss of lives. Ash flows, mud flows, they can overwhelm populated areas. These things can pollute the environment to the extent that when we inhale them, they can affect the respiratory system. Okay, landslides, floods, we all have an idea of how geologic hazards can affect us, and we are all part of the earth, and all of these things can happen around us. So there's a need to study why they occur, how they occur, and what we can do when they are occurring. What are some of the branches of geology? We are saying geology is divided into two broad fields. The first is the physical geology, and the other is the historical geology. Physical geology talks about what? the earth materials and processes that operate on those materials. Okay, so this include mineralogy, a study of minerals; petrology, a study of rocks. Petrol is not petroleum. Okay, petrol is from the Greek word petros, which means rock. So it's a study of rocks. Okay, geomorphology talks about the various landforms within or on the earth. Geochemistry, study of chemistry with relation towards the earth. Geophysics, application of physics to the earth. Sedimentology, how sedimentary activities take place. Okay, structural geology, the various structures we see within the rocks and then at various portions of the earth. Okay, economic geology, how we can leverage on economic resources such as the minerals in the earth. Okay, then engineering geology, the application of geology within the engineering practice. So for instance, you want to put up a structure on a particular site. Once that structure is within a soil, within a rock, you would have to apply the knowledge of geology into the engineering of such a structure. Historical geology, that deals with historical development of the earth from the study of its rock. So we want to find out the things that happened in the past, alright, so that we can find a way of relating it to what is going on in the current life. So some of these are paleontology, study of ancient life. Okay, stratigraphy, study of the arrangement of rocks. So that will give us an idea of which one is younger or older based on the way they are arranged or aligned. Then paleogeography. Paleo also, as we mentioned, refers to ancient life, and then geography talks about the graphical presentation of what happens. Okay, so paleogeography talks about the graphical presentation of the ancient lives within the earth or on the earth. Okay, and then geologic mapping gives us an idea of how to map, how to find out how a particular geologic unit is behaving, whether it is folding or it is dipping in a particular direction. We want to find out how much of that is going on, whether it is 20 degrees, 30 degrees. Okay, so geologic mapping also gives us an idea of the things that happened in ancient time with respect to the earth formation. Alright, so what are some of the early ideas about the formation of the earth? The early ideas of the earth were based on arbitrary pronouncements without keen observations and experimentations, as is done in modern day science. So sometimes people just look around and they are like, okay, based on this and this, I believe this is what happened to result in this. Okay, so you can just make arbitrary pronouncements without any keen observation. So you wouldn't have done any experiment, you wouldn't have observed anything from an experimental process. Okay. Bernard Palissy, who is a French scholar and lived in the 16th century, believed that the earth was much older than some people were speculating around that time. Why? Because his observations that the rain, the wind, and the tides were the cause for much of the present day appearance of the earth. He wrote that these forces, the forces that generate the rain, the wind, and the tides, could not work over a short period of time to produce the changes that we see. So, what are some of the changes? For instance, you see that a sediment or a material is moved from one place to the other and deposited over a long period of time, and it is that deposition, continuous deposition, that will result in formation of a rock, for instance a sedimentary rock. Alright, and then rain and wind and then tides could usually be some of the media through which these sediments could be transported. And we realize that this would usually take a longer time than some people were speculating. He was burnt at the stake, okay, in a prison in 1589. Then we have in the 17th century Archbishop Asher from Ireland, who based his genealogy in the Bible to determine that the earth was created on October 26, 4004 BC at 9 a.m. PST. Therefore, the earth is now over 6,000 years old. So he based his age on what? The genealogy of the Bible. What is genealogy? Finding out the various age ranges of the different generations that lived on earth based on biblical accounts. So you go to Genesis chapter 5, you can see a lot of that there. You go to Genesis chapter 10, you see some of those things. Chapter 11, even Matthew chapter 1, you will see some of those things. That is what he believed, okay, based on Archbishop Asher's idea of this calculation. He calculated and realized that, okay, BC 4004, BC is what? Before Christ came. 4004 years before then was when the earth was formed. So he based the creation of the earth based on what? The biblical account. And so after Christ came, up to now, another 2,000 years. So 2,000 plus 4,000, we are saying the earth is what? He is saying, per his account, the earth is about 6,000 years old. Alright, that's another person's opinion. Then in the 18th century, we have James Hutton, who is now referred to as what? The father of geology, a Scottish man. He published the theory of the earth, okay, in 1785. He suspected that the earth was older than the 6,000 years that Archbishop Asher was proposing. Why is that? He based his observation on the principle of uniformitarianism. What does it state? The principle of uniformitarianism states that the physical, the chemical, and biological laws that operate today also operated in the geologic past. The physical, chemical, and biological laws, the various laws that govern physics, chemistry, biology, that are operating today have also operated in the past on the earth. In other words, the forces and processes that we observe shaping our planet today have been at work for a very long time. Thus, to understand ancient rocks, if you want to understand ancient rocks, we must first understand the present day processes and their results. This idea is commonly stated as the present is the key to the past. So, in a nutshell, what is the principle of uniformitarianism? Uniformitarianism. It is what states that the present is the key to the past. The processes that are going on presently are giving us an idea, give us a clue to what went on in the past. Alright. Hutton observed that a certain type of rock called sandstone is composed of sand grains cemented together. So you can see here, this is an example of a sandstone. Sandstone. You know what a stone is. We are saying that this stone or this rock is made up of what? Sand. And sand, you can fetch sand in your hand. It's just soil. Okay, there are different types of soil. We have clay soil, sandy soil, and all that. So sand make up soil. And then Hutton observed that this rock, which is sandstone, is composed of sand grains cemented together. What is cement? Something that binds or holds things together. He also noted that rocks slowly decompose into sand. So after we've gotten a sandstone, which is the rock, it does what? Decompose into sand, which is now the sediment or the soil. And that streams carry the sand into the lowland. And he inferred that sandstone is composed of sand grains that originated by the erosion of ancient cliffs and mountains. So these are some of the ideas that James Hutton used to come up with the principle of uniformitarianism, to give us an idea of the present being the key to the past. Now we come to the principle of catastrophism as proposed by Cuvier and Whewell in the 1700s. The principle of catastrophism briefly states that Earth's history has been dominated by cataclysmic events rather than gradual processes acting over long periods of time. What are they trying to say? Features such as mountains and canyons, which today we know to take great periods of time to form, were explained as having been produced by sudden and often worldwide disasters produced by unknown causes that no longer operate. So, for instance, in the case of catastrophism, Cuvier and Whewell are saying that mountains, alright, you see a mountain, you see a canyon. A canyon is like, let me see if I can sketch it. A canyon is this kind of pathway. So you find a rock, a whole rock body this way, another rock body this way. Okay, then this is like a way, a channel through which you can pass. So this event of this rock body giving way, okay, maybe initially they were together occupying this place, then something happened and then they are splitted apart. Cuvier and Whewell are saying that mountains and then canyons are formed by what? Catastrophic activities or cataclysmic events. They happen suddenly. They did not take any long time to occur. They just happen all of a sudden. Something just pushed against the other one and then a mountain formed. Something that just divided an existing mountain, and then this one splitted here, this one also splitted here immediately. It didn't take any long time at all. It just happened all of a sudden. Meanwhile, along the line, you study and know that no, these landforms or these features on the land occurred as a result of what? Gradual processes. Okay, they occurred as a result of gradual processes that act over a long period of time. So, on a whole, the principle of catastrophism has so much doubt and is not really accepted in the world of geology. Alright, we are still continuing with the age of the earth. Now there's what we call radioactivity. I'm sure you guys all did chemistry back in school, so you remember what radioactivity is. So as it was discovered by Henry in 1896 and also in 1905, Rutherford and Boltwood used a radioactive decay to measure the age of rocks and minerals. For instance, they realized that if uranium decays, it produces what? Helium. And the and this leads to dating of what 500 million years of the oldest rock. So at that time they are saying that okay, when they were able to measure some of the rocks and minerals using uranium dating, which produced helium, they found out that some of these rocks were about 500 million years old. And then in 1907, Boltwood suspected that lead was the stable end product of the decay of uranium, and then he published the age of the sample of uraninite based on uranium lead dating to be what 1.6 billion years. So it kept progressing. They kept discovering that with the use of isotopes they can find out the ages of different rocks, and then in 1905 they came up with this. In 1907 they came up with this also. Now, based on the most current form of dating, you are saying that the oldest dated rocks on the earth are 3.96 billion years. Okay, and this rock is what? The Acesta gneiss, which is found in Canada. Alright, so the oldest rocks on the earth have been found to be dated to be how many years old? 3.96 billion years. However, there are older rocks. There are rocks that are still older than this 3.96. There are older rocks which include meteorites and moon rocks. So meteorites, they are other celestial bodies that have found their ways onto the earth, and also moon rocks, rocks on the moon, where the moon rocks from the lunar highland are about 4.5 billion years old, and that was the period where the earth was being formed. Alright, and that was the time where the moon was also formed. So some of the rocks from the moon were dated and found out that it was what 4.5 billion years. And since the earth was also formed around that period, scientists are currently saying that the age of the earth is what about 4.54 billion years, plus or minus 0.05. Origin of the earth. So we would like to look at what the universe is. What is the universe? The universe is everything. Everything. It includes all of space, all the matter, all the energy, and the space it contains. It even includes time itself, time. And of course, it includes you. So everything that we can think of, anything that you can think of, makes up the universe. The earth and the moon are also part of the universe, as are other planets and their many dozens of moons. Along with asteroids and comets, the planets orbit the sun. So the planets orbit the sun, they all go around the sun. The asteroids and comets, they also do the same. The sun is one among hundreds of billions of stars in the Milky Way galaxy. So there's a Milky Way galaxy, and we are seeing that the sun is just one of the hundreds of billions of stars in the Milky Way galaxy, and most of those stars have their own planets known as what? Exoplanets. The Milky Way is but one of billions of galaxies in the observable universe. So the universe, as we mentioned, the universe is everything, and we are seeing the Milky Way, of which our solar system is just part of it, is what? Is just one of the billions of the galaxies in the universe. The Milky Way is estimated. It is estimated that there are between 200 billion to 2 trillion galaxies in the observable universe, which tells us that the universe in which we find ourselves, you can barely locate the Earth or even our solar system because it is very large. Okay, and that is even with the observable universe. It's possible that there is an unobservable universe and a part of the universe that is probably not visible. Now, I want to talk about the Big Bang theory and nebula hypothesis. A nebula hypothesis is an explanation for the formation of a solar system, whereas the Big Bang theory explains the origins of the universe. So we had already mentioned that the universe is everything and the solar system is just one part of the universe. Okay, however, the nebula hypothesis explains how the solar system was formed, which is just a subset, a subset of the universe, and then the Big Bang theory explains how the universe was formed. Let's look at the Big Bang theory. It states that the universe began as a tiny dot, dense point called a singularity. So the Big Bang theory is saying the whole of the universe in which we find our solar system, and our solar system also includes the Earth, includes the Sun, the whole universe began as a very tiny, hot, dense point, like a point like this. A point like this, a dot. Said everything was like a small dot like that, and it's referred to as what? Singularity. This singularity contained all the matter and energy that would eventually form the universe. So they are saying that the singularity, the small, hot, dense point, contain all the matter and energy. You can imagine all the things we are seeing around us and in other planets that we can't even have access to. All of that were found in what? The singularity. About About 13.6 billion years ago, the Big Bang created the universe from a point. Okay, from a point source. During this process, light elements like hydrogen, helium, lithium, boron, and beryllium formed. So in this case, we are saying that this little dot or this little point source began in what? 13.6 billion years ago. That was when it was created. And then during the process, it includes, or it has helium, hydrogen, lithium, boron, and beryllium forming. At this point in time, the universe began to expand and has been expanding ever since. Concentrations of gas and dust within the universe eventually became galaxies consisting of millions of stars. Within the larger stars, nuclear fusion processes eventually created heavier elements like carbon, silicon, calcium, magnesium, potassium, and iron. Stars eventually collapse and explode during an event called a supernova. During a supernova, heavier elements from iron to uranium are formed. So you see the sequence. At the beginning, it It was a small dot or a small point source which contained which formed helium and all these other elements. Then from that point it began to expand, and it has been expanding ever since, that little point source. As it began to expand, we are seeing that there were concentrations of gas and dust within the universe that eventually formed the galaxies that we are talking about, that form the universe. And these galaxies consist of millions of stars. So a galaxy is made up of millions of stars, and these stars could be very gigantic. They are saying within the larger stars, nuclear fusion processes created heavier elements like this, the ones we mentioned. Okay, and then these larger stars become eventually collapsed. All right, the larger stars eventually collapse and then they explode during an event called a supernova. So that's it with the Big Bang theory. A point source that was existing, which included or made up of elements like helium, hydrogen, lithium, boron, beryllium, and the rest, and also eventually was expanding into gas and dust, then made up other elements, and then the creation of stars, the creation of the galaxies. Then along the line it has gotten to the point where humans and other things have been formed from the earth and other planets. Now we move on to the nebula hypothesis. If you remember earlier, we said the nebula hypothesis talks about the formation of the solar system, whereas the Big Bang theory talks about the formation of the universe. Okay, now the solar system is where the earth is located. So all the other planets, including the sun, that were formed within that process, all have the same age. Okay, so it is believed that the earth and other planets were formed at essentially the same time. The hypothesis of the Earth's origin states that close to about 5 billion years ago, the matter that became our solar system was an immense, diffuse, frozen cloud of dust and gas called the nebula, which rotated slowly in space. So we are saying that at the beginning of the formation of the solar system, there was a cloud of dust and gas, and this is referred to as the nebula. You remember, with respect to the Big Bang, that dot or that point source, we refer to it as singularity. But in the case of the nebula hypothesis, which is for the solar system, the gas and dust cloud is referred to as nebula, and this was just rotating slowly in peace in space. This cloud formed from matter ejected from an exploding star. More than 99% of the cloud consisted of helium and hydrogen. So if you remember, in the case of the Big Bang, also we mentioned that helium, hydrogen, lithium, and the rest were all part of the elements that formed it. Now over here we are saying that more than 99% of the composition of the nebula is hydrogen and helium. And this is because these two elements are the most abundant elements in the universe. More than 90% of the matter in the cloud collapsed toward the center of the disk under the influence of gravity. So this dust and gas cloud called a nebula, which contains hydrogen and helium, got to a point that made it to what? Collapse towards the center of the disk. So if there is a movement towards the center of another material on Earth or in our solar system, we refer to it as what? Gravity. Alright, so this process where the existing gas and dust, which were just somehow scattered, now started moving towards the center of the Earth center of the solar system based on gravity, forming the protosun, the earlier version of the sun. Throughout the galaxies, clusters of gas attracted by gravity start to rotate and accrete to form stars and a solar system. So as there is this continuous movement of these gas and dust particles towards the center of the Earth, it resulted in some form of rotation of these materials. So as these materials were rotating, they were getting accreted, or there was some form of accretion. They were running into each other at some portions, and as they kept running into each other at various portions, they started forming some small bonds among themselves, and this resulted in the formation of what? Stars, and then eventually the solar system. The ball at the center. So as these materials continue to move towards the center and were also rotating, the ball at the center grows dense and hot. So because of the kinetic energy, once there is motion, there is the collision of materials towards each other, there will be that form of what? Heat creation. Alright, so these materials began to focus more within the core or the center, and based on gravity, the heavier materials will be the ones that will be attracted towards the center, whereas the lighter ones will still be hovering around. Okay, so the heavier ones resulted in the growth of the dense material, and then as there is also continuation of collision and accretion of materials, there is also an increase in temperature, which makes it hot, and it eventually resulted in what? The nuclear fusion reactions. Okay, and this is in our case that formed the sun. So the nuclear fusion reaction that couples with the gravity. So nuclear fusion reaction talks about how hydrogen atoms would crash into each other, forming helium. Okay, and this would generate so much heat and so much pressure that they would want to diffuse out, okay, go away in a divergent form, like they are trying to rather spread out. So as gravity is trying to pull the materials towards the center, nuclear fusion is also trying to what? Make the materials go further away, and this is what results in equilibrium of what? The sun. It doesn't make the sun to spread out, to scatter out, and it doesn't make the sun to shrink in. So it results in some level of equilibrium. And we are saying here in the 6th point that the rings of gas and dust orbiting around the sun eventually condense into small particles. These particles are attracted to one another, and larger bodies called planetesimals begin to form. So there's now the formation of a ring of gas and dust, while the materials keep doing what? Orbiting around the sun. So the gravity is still in motion, they are still moving around, and then they are saying as this is going on, they condense into what? Small particles, and these small particles are attracted to one another, and the larger bodies called the planetesimals. So these bodies are the ones that are larger as compared to the other ones, and they are the ones that eventually form the planets. Okay, so the planetesimals accumulate into a larger mass, and this larger mass form what? Irregular shaped materials or objects, referred to. One of them formed what? The proto-earth. Okay, proto-earth, the baby earth, or the initial stages of the earth, where then the interior heats up and then becomes soft. So as I mentioned earlier, as there is continuous heating or collision of the materials, there is what? Increase in temperature because of the kinetic energy that will take place. So as the heat increases, the materials at the interior, some of them become what? Soft, or they become molten. Gravity shapes the earth into a sphere. The interior differentiates into a nickel iron core and a stony silicate mantle. So when we look at the layers of the earth, you realize that the earth is made up of a core, which is basically composed of nickel and iron, which are the densest materials, and then we have the stony or the silicate ones making up what? The mantle. Then soon a small planetoid collides with Earth, where debris forms a ring around the Earth. So there's a body that now comes to collide with the Earth, and then you see the debris coalesces and forms what? The moon. So at a point it looks like the whole surface of the Earth was made up of molten rocks, okay, because there was still the movement of these particles that were having very high temperatures, okay, and then so this resulted in some of the gases forming, and these are volcanic gases. All right, when the Earth becomes cool enough, the moisture condenses and accumulates, and then the oceans were born. So that is how, based on the nebula hypothesis, the oceans came about. Okay, so I'm hoping this figure here would give you a power summary of the nebula hypothesis. So you look at the first one, you are seeing that's where the dust and the gas cloud was formed, and this is composed of what? Hydrogen and helium elements. All right, and this is suspending somewhere and then gently rotating, scattered somewhere in the universe. Then at the second point, you are seeing what? It collapses towards the center by gravity. So initially they were just all suspending there, but then at the second point they began to what? Collapse or coalesce towards the center by what? Gravity. Gravity is what pulls materials towards the center. All right, so when this started happening, the materials were moving towards the center, but not directly towards the center, but then they were moving in an orbital form, moving towards the center in an orbital form, and this resulted in what? A disc-like shape. All right, so that's it, as we can see in the second phase. And in the third phase, you realize that a mass groups into a discrete protoson. So the protoson, where the sun had not yet been formed, but then it is starting to form. All right, and that's where the different materials begin to crash or collide into each other, and they started forming the various planets. But then at that point they were also what? Not yet fully formed planet. They were gradually getting collided into each other, getting attracted towards each other as they were moving towards the center and orbiting around the protoson. And then as the process continued, at the fourth stage we had the sun fully forming, and then the other planets forming, and were all and are all rotating or orbiting around the sun. Okay, another summary. So as we can see from the figure here, A, B, C, D, E. You are seeing for the A, the solar system was originally a diffuse cloud of dust and gas. In the B, we can see that this dust and gas began to coalesce or move or gravitate or find their way towards the center as a result of gravity. Then the third stage is where there was shrinking of the mass. Okay, there began a shrinking of the mass, and it made it to rotate and to form a disc-like shape. Then at the fourth stage, the mass broke up into a discrete protoson. So at that point, we can see that the protoson is trying to take shape, and it is showing the other smaller planets that, yeah, I am the big guy. You guys, you should see that there's a difference between you and me. Even though at that stage it had not yet become the sun, it is still at the baby stage, but then it is able to properly distinguish itself as a discrete material. And even at that stage too, the other materials or the other protoplanets, which had also not yet fully formed planets, were orbiting around it. Then at the fifth stage, the sun heated until fusion temperatures were reached, where the heat from the sun drove most of the hydrogen and helium away from the closest planets, leaving small solid cores behind. Okay, so it's trying to say that the hydrogen and the helium that were very major components during the formation of the solar system were driven away as a result of what? The heat. So they were pushed further and further away from the sun. And then it left behind what? The solid cores. So these gases or less dense materials were pushed further away, and then the highly dense materials were rather closer to the sun, forming the planets that are closer to the sun. The massive outer planets are still composed mostly of hydrogen and helium. So the outer planets, the ones that are further away from the sun, are mostly composed of helium and hydrogen, whereas the ones that are closer to the sun have more of the solid materials as well as other liquids and gases. Okay, what is the current or the modern appreciation of our solar system? We are saying that we group the solar system into two. The first part is a terrestrial planet, and then the other part is the Jovian planets. What are the terrestrial planets? We say the first four planets that are closest to the sun, which are Mercury, Venus, Earth, and Mars. They are mainly rocky and are called the terrestrial planets because they are Earth-like. Even though they do not have all the beautiful properties that Earth has, the fact that they are having more solid rocky materials, we refer to them as the terrestrial planets. Then the outer four, Jupiter, Saturn, Uranus, and Neptune form the Jovian planets. It's not like they are Jovian. They like making jokes. Okay, they are composed primarily of liquids and gases with small rocky and metallic cores. So they may also have some form of metallic cores and some small proportion of rocky materials, but then their primary composition is the liquids and the gases. As we mentioned earlier, the hydrogen and the helium were pushed further away, and then they will be found around or within these areas. So that's it with the formation of the earth, the age of the earth and the solar system, the origin of the earth, the universe, and all that. So we talked about catastrophism, we talked about the uniformitarianism, and we came to talk about the universe, okay, and the nebula hypothesis. The universe, we talked about the Big Bang theory, the nebula hypothesis about the solar system, and then the various ages as the Archbishop proposed based on the biblical genealogies, and then other people based it on the fact that the rain and the wind and those actions would certainly show that the earth was way older than what is being suggested. And then radioactive materials now started to take the stage, where radioactive dating was used to date the earth or the rocks, and then it was found that the oldest rock is close to 4 billion years, which is found in Canada, the gneiss. Okay, so yeah, there are different theories, but then some of them make up or make a whole lot of sense as compared to the others. So as geologists, we just say, okay, this one makes more sense, especially using the theories of science, physics, chemistry. All of this make some of this make a lot of sense, and we just go by them. Okay, now we come to the spheres. The spheres that make up the earth. We are seeing that there are 4 major subsystems that make up the earth. So all of them are referred to as spheres. Atmosphere, hydrosphere, biosphere, geosphere. Atmosphere. Okay, atmosphere refers to what? The gases that envelope the earth. Hydrosphere, hydro, refers to what? Liquid materials, right? So the rivers, the ocean, the glaciers, the lakes, okay, they refer to what? The hydrosphere. A glacier may not presently be in a liquid state, but then it is water. Okay, water that is in a solid state, it's still water, and hydro means water. Okay, water, so hydrosphere refers to water on or near the earth's surface. Biosphere, biology, biosphere, living things, so all living or once living materials in or on the earth. Then geosphere, which refers to the solid rocky earth. The solid rocky earth. So among these 4 spheres of the earth, which one do you think geologists would be more interested in? Beautiful. I'm sure your guess is as right as mine. The geosphere, because we are interested in studying the solid rocky earth, not the atmosphere, not the gases, not just the hydrosphere, the water, not just the biosphere, living organisms, but then the solid rocky earth. Okay, so a little more focus on each of them. So the hydrosphere, so it includes water that is found in streams, in wetlands, in lakes, in the oceans, and sometimes there's some little water in the atmosphere. Okay, that's the water that finally releases as what? Precipitation. And frozen, and some of the waters are also what? Frozen in glaciers. It also includes groundwater, which refers to water present in soil and rocks. Okay, and they could be very deep, but then once it is water, we are referring to it as what? Part of the hydrosphere. Then the atmosphere. So the atmosphere is a mixture of gases, mostly nitrogen and oxygen. The atmosphere is held to the earth by gravity. and thins rapidly with altitude. So if we are on the ground, you look up, you see that the atmosphere looks nice, the clouds are thick and all that. But if you approach it gradually towards the sky, maybe you are in a plane and you are getting closer to the atmosphere, you realize that they are not as thick as you may be imagining them while you are on the ground. 99% is concentrated within 30 kilometers of the Earth's surface. So we are still referring to the atmosphere. But a few traces remain even 10,000 kilometers above the surface. A brief look at other planets reminds us that the interactions among air, rock, and life affect atmospheric composition, temperature, and movement. And now to the biosphere. And now the biosphere. The biosphere is the thin zone near the Earth's surface that is inhabited by life. Within the biosphere, living things from ecological communities based on the physical surroundings of an area. Okay, so it's basically referring to what areas that are occupied by living things, of which human beings are part. We have the plants, we have animals, we have birds, we have fishes, all of the things that are living things within the earth, whether they are bacteria, fungi, microorganisms, whether they are on the sea floor or on the land or in the soil, wherever they are. Once they are living organisms, we refer to them all as what? Part of the biosphere. Then the geosphere. Beneath the atmosphere and the oceans is the solid earth, or the geosphere. The solid, semi-solid, and liquid land form layers that are physically and chemically different. So we have the solid state, we have the semi-solid state, and we have the liquid state of land. And we are saying all of these words form layers that are physically and chemically different. It extends from the surface to the center of the planet, a depth of about 6,400, earlier we said 6,370 kilometers, right? Making it by far the largest of the Earth's 4 spheres. Okay, so we mentioned earlier that the atmosphere takes about 30 kilometers of the Earth's surface, but then here we are seeing, and then the biosphere doesn't go really deep, maybe a maximum of 10 kilometers, which I even doubt. Then the hydrosphere may be up to about 2 kilometers, but then with the geosphere we are seeing it goes up to about close to 6,400 kilometers, and it makes it the largest of the 4 spheres, the thickest of the 4 spheres, the one that has the highest proportion when it comes to thickness or volume with respect to the Earth. The geosphere contains all of the cold, hard, solid land of the planet's crust, which is the surface or the nearest to the surface material of the Earth, the semi-solid land underneath the crust. So right under the crust we have a semi-solid material, and then the liquid land near the center of the planet and the surface of the geosphere is very uneven. So he just tried to describe how the different layers are: the very solid first layer, the semi-solid second layer, the liquid third layer, and then there's another one which is also a very solid layer, okay, which is the core. We are saying the surface of the geosphere, the surface where we walk on, is very uneven. So that's how come we have valleys, we have mountains, we have ridges, we have rifts, we have the canyons and different landforms. All right, there are high mountain ranges, huge plains of flat areas, and deep valleys along the ocean floor. So there are different landforms which make the geosphere to be uneven. The Earth system: the atmosphere, the biosphere, the hydrosphere, and the geosphere, and all their common components can be studied separately. However, the parts are not isolated, as each is related in some ways to the other to produce a complex and continuously interacting whole that we call the Earth system. The hydrosphere is related to the geosphere, geosphere is related to the biosphere, biosphere is related to atmosphere. All of these spheres or these systems of the Earth are related to each other. So we can't just say, oh, the atmosphere is an independent guy, he doesn't rely on anyone. No, the atmosphere relies on the hydrosphere, because unless there is an evaporation of the water on the surface of the Earth, which is the hydrosphere, we will not get the clouds, which are the atmosphere, which make a part of the atmosphere. Okay, and then unless there is a geosphere, if we don't have a solid ground, if we don't have the earth, if we don't have the soils, there will not be any crops, there will not be any animals, there will not be any human. What will we survive on? So all of this interchangeably rely on each other. The Earth system is powered by energy from two sources: 1, the sun; 2, the Earth's interior. The sun drives external processes that occur in the atmosphere, the hydrosphere, and the Earth's surface. And then I think we've omitted the fact that the sun also influences the biosphere, because humans and plants rely heavily on the sun. Weather, climate, ocean circulation, and erosional processes such as rivers, glaciers, wind, waves are driven by energy from the sun. The sun controls a whole lot of activities on the Earth's surface. Okay, so anything or most of the activities that take place on the surface of the Earth, where we find the hydrosphere, the biosphere, the atmosphere, and the portion of the Earth's surface, which is the shallow portion of the Earth's surface on which the biosphere also exists, we say what? They are being influenced or driven by the sun. Then we have the Earth's interior, which is the second source of energy. The heat remaining from when our planets formed. We just finished talking about the nebula hypothesis, right? And we were saying that during the formation of the Earth, or during the formation of the solar system, the collision of the various materials resulted in the generation of heat. Okay, we are saying the heat remaining from when our planets formed, and the heat that is continuously generated by decay of radioactive elements powers the internal processes that produce volcanoes, earthquakes, and mountains. So you've seen that they've mentioned two sources of energy from the Earth. Okay, They are saying that the Earth's interior generates what? Two forms of energy, or two forms of heat energy. The first one is what? The heat remaining from when our planets formed. We refer to that as the accretional heat. Then the heat that is continuously generated by the decay of radioactive elements. That one is what? The heat from the radioactive element, radioactive heat. Okay, so these two forms of heat power the internal processes that produce some of the activities like what? Volcanoes, earthquakes, and the generation of mountains. Both the external and internal processes could contribute to either slow or fast processes acting upon both the surface and within the earth. What are some of the examples of slow processes? Formation of rocks. It takes a long time for a rock to be formed. You can imagine, which type of rock do you know? Is it igneous? Is it sedimentary? Is it metamorphic? Let's pick any of them. Let's pick sedimentary for instance. For the rock to be formed, there should surely be an existing rock. And that rock is probably very hard, and the components or the minerals are very compacted and knitted towards each other. Before there would be sediments, there should be weathering. And weathering is the breakdown of the rocks into smaller particles or into sediments. So the weathering process alone can take hundreds of thousands of years. After this process, we now have sediments. These sediments need to be transported, whether by wind or by water or by whatever. They would have to be transported. This transportation can also take hundreds of years. Now, after the transportation, there will now be deposition. You will now deposit it, but you realize it is still in the sediment stage, the loose state, the unconsolidated stage. So these materials will now get deposited one over the other set. Another set is depositing over each other, and this process can take another set of hundreds of thousands of years. Then we now have, or we get to the stage where these materials or sediments will begin to compact under the force of gravity or under the influence of gravity. When this compaction is taking place, that's when the air spaces or the voids are taken out. We will soon be talking briefly about sedimentary rock. When you get there, I'm going to skip because I'm just talking about how sedimentary rocks are formed. So when there is a continuous deposition, there is gravity influence, it results in the termination or the removal of air spaces, so that the solid sediment materials would fill up all the air spaces or the voids and then compact properly. So that stage is called compaction. Alright? During the process of compaction, there's another process that triggers, which is referred to as cementation. So as these sediments are getting to knit or getting to bond towards each other, there are some chemicals that are excreted or that are released that serve as cements, that serve as bonding agents to bind these sediments together and make them become a rock. So this all can take by the time you finish, it has taken about maybe some tens or hundreds of millions of years to be formed. So these are very slow processes. Chemical breakdown of rock to form soil, we've already talked about that, can take a very long process, weathering. Chemical cementation of sand grains together to form a rock, we just talked about that. It takes a very long time. Recrystallization of rock to form a different rock, we refer to it as metamorphism. So let me take this opportunity to also talk about metamorphism. So metamorphism refers to the conversion of an existing rock into a metamorphic rock. Alright, so usually you would have an igneous rock or a sedimentary rock, and sometimes the earlier version of a metamorphic rock, but usually let's just stay focused to our igneous and sedimentary. So these two rocks are in existence, and then if these materials find their way deeper into the Earth's crust, the deeper they go, the higher you go, the cooler it becomes. The deeper you go, the hotter it becomes. So as these materials, sedimentary or igneous materials, keep going deeper, maybe as a result of tectonic activities or any geologic activities, they find themselves going deeper into the subsurface, into the Earth's crust. Then heat begins to impact them. As the heat begins to impact them, their lives will never remain the same again, because you were formed at the cool state. You finally got formed at the cool state, but now you are getting to a hot state, and that will rearrange or reorganize you. Just like you were probably in high school or GHS, you are not bombarded with things like the differential equation. Yeah, maybe some of you have done calculus, so you are now fine. But then at the university level, there are higher dimensions, and you keep getting higher and higher. And you realize that, Charlie, the thing I learned at SHS or GHS, Charlie Sana, that one crowd was low level crowd. Your brain is now being realigned because the pressure is increasing, the heat is increasing, it is getting tensions. So as the heat is increasing, you realize that your brain will now be realigned. There will now be an adjustment of your brain in a different dimension to grasp it at a higher level. It is the same thing that the rocks go through when they are undergoing higher heat or greater temperatures. The mineral grains begin to realign themselves. At the initial stage, maybe they were just scattered all over, but then when the heat begins to set in, when the pressure begins to set in, you know that when you get to the surface of the earth, the pressure is not that high, but when you go deeper, the pressure is higher. Okay, the deeper you go, the higher the pressure. The deeper you go, the higher the heat or the temperature. So as it keeps going deeper and deeper, the temperature increases, the pressure increases, the minerals will also change. They would go through some form of maybe deformation or some form of changes. Okay, and this will usually result in a realignment or the bringing up of some newer minerals. Okay, and this is what we refer to as a recrystallization of a rock to form another rock. When the existing minerals recrystallize, they go through a rebirth, okay, to generate new crystals. That is what we refer to as metamorphism. And this would also take a very long time, and it is certainly a slow process, not a fast process. Then we have the construction of mountain ranges, where mountains are formed as a result of tectonism, and as opposed to the theory of catastrophism, the mountains are not formed just instantaneously. They are formed as a result of slow processes of tectonism. We'll be looking at plate tectonics, and you understand it clearly. These are very slow processes. Okay, then we have the erosion of mountain ranges. It takes a very long time for a mountain range to be eroded. So what are some of the fast processes? The fast processes include the beach erosion during a storm. So you look at the state of a beach, you see the beach sand, then there is a storm. Quickly, once that storm is having that high velocity, it can easily take up that beach and then erode it and make it move from one place to the other. We also have the construction of a volcanic cone. So when there's a volcano occurring, you realize that there is some form of cone-shaped formation when the lava is flowing or the magma is trying to find its way towards the surface to let the lava flow. So when the lava begins to flow on the surface, you would find that there's a conal shape, and that is relatively a faster process. Then we have landslides, for instance avalanches. These are things that occur within very short moments, okay, and dust storms and mud flows. These are things that happen very quickly as compared to very fast process, very slow processes. Okay, a dust storm, within some minutes you see that the whole area is full of dust, okay, and then the mud flows, they also follow suit, and this could be very dangerous where they can take along some structures while they are flowing. Processes such as these are constantly acting upon and within the earth to change it. Many of these processes are cyclical in nature. The parts of the earth system are linked so that a change in one part can produce changes in the other parts. Let's look at the water cycle. Water cycle. The mass of water on earth remains fairly constant over time, but the partitioning of the water into the major reservoirs of ice, fresh water, saline water, and atmospheric water is variable depending on a wide range of climatic variables. So we are saying that basically the water we find within the earth, okay, or in the earth's domain, in the earth system, whether it is within the hydrosphere, the biosphere, the atmosphere, or the geosphere, wherever we find water, we are saying that it's basically what? The same, just that they are partitioned or they are divided into various proportions within the various reservoirs, okay. Some of them could be saline water, for instance the sea is what? Saline water, lots of salt in it. We have fresh water, which could be in lakes or rivers or streams or borehole water or groundwater, and then we have atmospheric water, water in the skies or in the atmosphere, and all of these are in what? Different proportions based on a range of climatic variables. Now, the water cycle. Water that is on the surface of the earth. So for instance, in this case the sea, or maybe a dam somewhere, or a river or a stream, all of these waters that are exposed to the atmosphere would go under the influence of the sun's heat energy. And what do you think would happen when the sun's heat energy reacts or has a role to play with the water on the surface? It will evaporate, right? So we have evaporation here. So evaporation is the change of state of matter from the liquid state to what? The gaseous state. So this water will now become gas and then rise into the atmosphere. It's not only through evaporation. When plants also give up their water, we refer to it as what? Transpiration. Okay, so transpiration will also take place where plants will also give out their own sources of water. Apart from that, we also have what? Sublimation. Sublimation is what? The change of state of matter from the solid state to what? The gaseous state. So this one doesn't have the chance to go through the conversion into water, or liquid, before it becomes a gas. Directly from the solid state, it becomes what? A gas. It sublimes. So that's it with the taking up of water into the atmosphere through evaporation, through transpiration, and through what? Sublimation. So this will result in what? A condensation along the line. So condensation means what? A change of state of matter from a gaseous to what? The liquid state. So evaporation from the liquid to the gaseous, because now these gaseous materials are going up into the sky, into the atmosphere, and you know the higher you go, the cooler it becomes. At the state where it was liquid, the sun's energy acted on it and it broke the bonds that were holding the water molecules together, so they could easily fly away into the gaseous state. Now that they have scattered around and then they are going up, they are ascending into the atmosphere, the temperature has become cool. Alright, so because it has become cool, it will now start to form droplets of water again. They will now start to reattach to each other again. Alright, so during the reattachment or the bonding of the water gaseous molecules towards each other, they will now form water droplets. And this formation of water droplets after the condensation is referred to as transportation. Okay, because the water droplets will form into a small clouds, and then these ones will also be transported into bigger clouds. So the condensation will result in smaller cloud formation. Then these smaller clouds will keep depositing. Another small cloud from somewhere will also deposit another small cloud, and that movement of the various smaller clouds into a bigger cloud is referred to as transportation. The same thing we are seeing over here. After the period of transportation, the clouds become very heavy. And if the clouds become very heavy, you know that at that point they have become liquids, and at the state where they are no more able to stay in the skies or in the atmosphere, they now fall back as rain. So you now see precipitation, rain falling back on the ground or onto the surface of the earth. And then in areas where the rain is not a liquid, okay, as we see in parts of Africa, in areas where it falls as solid or snow, we refer to it as deposition. Okay, deposition. All right, so deposition or precipitation is when the water or there's a release of water, whether in a solid or liquid state, onto the ground. So we talked about water going into the atmosphere. Now we talked about water coming onto the surface. So when it gets onto the surface again, it joins the surface runoff or surface flow. Okay, sometimes so there is snow melt runoff. So some of the snows will be running off along the hills, and then other water bodies may find themselves or their ways towards other bigger water bodies, maybe a dam based on the elevation. When there is a lower elevation or a catchment, they all move towards that direction, but eventually most of the moving water or surface runoff move into the sea. So some of the water runs on the surface, some of them goes into the sea, some of them are evaporated, and some of them go into the ground. Alright, so this one is going into the ground, the ones that are not able to flow away. So once they are going into the ground, we refer to it as infiltration. When water begins to move into the ground, we refer to that as infiltration. And when it gets to the point where you are getting sufficient water in the groundwater system, then infiltration, percolation, they are virtually referring to the same thing. Okay, infiltration, percolation, water moving into the aquifers or finding their way into the groundwater system. Okay, so water now in the groundwater, or water in the ground, or water in the earth, water below the surface of the earth, which is as a result of infiltration and percolation, is referred to as groundwater. Okay, and this is what we could drill and then get borehole water from it. But they also find their way towards the sea, because the sea has a lower elevation, and then groundwater also moves. Groundwater is not stationary at one place. So once it's an aquifer and the aquifer is permeable, it will always try to find its way towards areas of lower elevation. Yes, so Basically, that's what the water cycle talks about. So if you remember, we talked about evaporation, we talked about condensation, transportation, precipitation, sublimation, transpiration, deposition, infiltration, percolation. Yeah, we didn't talk about plant uptake. So some of the water that goes into the ground or into the soil is taken up by plants. Alright, and that's what the plant will make use of, and then eventually give it out again, portion of it out through transpiration. Alright, so that's basically what the water cycle is about. The water doesn't go out of the system, it just keeps recycling. It goes to this stage, comes to this stage, goes again. Whether it enters the groundwater system, it still finds its way out, and then it keeps joining the water cycle. Now the rock cycle. So geologists group rocks into three categories on the basis of how they form: igneous, sedimentary, and metamorphic rocks. Under certain conditions, rocks of the upper mantle and lower crust melt, forming a hot liquid called magma. So they are saying that the earth has layers. Let me use this. You are seeing the earth has layers, and if the one on which we are standing is referred to as the crust, okay, certain condition, the rocks in the upper and lower crust melt forming hot liquid. Okay, so the crust, and then we have a portion called the mantle, and in the mantle we have what? Molten rock that is in the molten state, that is in the fluid state. Alright, under certain conditions of the upper and lower mantle crust, forming a hot liquid called magma. An igneous rock forms when magma solidifies. So this magma over here in the mantle, when it tries to find its way out of the mantle, alright, or of the magma chamber, and it cools down outside somewhere else. It could be on the surface of the earth, it could also be somewhere within the crust. Once it cools down and it solidifies, we see what? There is an igneous rock formation. And they are saying that about 95% of the earth's crust consists of what? Igneous rocks, and metamorphosed igneous rocks as well. So igneous rocks and metamorphosed igneous rocks. Granite and basalt are two common and familiar igneous rocks. So these are rocks that you'll be hearing of or seeing at a lot of places within the earth's crust. Sedimentary rocks. I think I mentioned that when I get sedimentary rocks, I'll not spend time because I've already talked about it. So I'm just going to do some reading. So rocks of all kinds decompose. The weather at the earth's surface. Weathering breaks rocks into smaller fragments such as gravel, sand, and clay. At the same time, rainwater may dissolve some of the rock. Streams, wind, glaciers, and gravity may erode the weathered particles. These weathered particles are referred to as what? Such particles form weathering and are eroded, transported, and deposited in layers are called sediment. Alright, these materials that have been weathered, transported, eroded, deposited are referred to as sediment. The sand on the beach and mud on the mud flats are examples of what? Sediment that accumulated by these processes. So a sedimentary rock forms when sediment, which may be a sand, a gravel, a dirt, when it becomes cemented or compacted into a solid rock. So as you can see here, When the beach sand is cemented, it becomes what? Sandstone. When the mud becomes cemented, it becomes what? Shale. Let me make it easier for you. When sand becomes cemented or compacted, it forms what? Sandstone. When so sand gives you what? Sandstone. Another one could be what? Clay. Clay will give you what? Yes, clay stone. There's a rock that you can refer to as clay stone. Silt is also another size of sediment. Silt, when it gets compacted and cemented, we refer to it as what? Siltstone. We also have mud. When it becomes compacted and then cemented, we have what? Mudstone. So most of these things, or most of these rocks that have these stone are what? Usually what? Sedimentary rocks. Okay, we have other examples. We have limestone, we have dolostone, alright, and probably a whole of other ones. But I'm not saying that it is only rocks that end with stone that are sedimentary rocks, because as you can see here, shale is what? A sedimentary rock. You also have another sedimentary rock called conglomerate. This is also not ending with stone. So there are other rocks that are sedimentary rocks, but then they may not end with stone. But then usually when you see the stone, it gives you an idea that this could be, not it is always, because you have to make sure that you take note of the material that is making up the stone. If it is clay that is making up the stone or the rock, then it's clay stone. If it is sand, which is also a sediment, then you say what? Sandstone. A silt, which is also a sediment making this up, siltstone. Mud making up the rock, refer to it as what? Mudstone. Be very careful, because there's a rock called let me clean this, guys. There's a rock called greenstone, or a group of rocks called greenstone. This is not a sedimentary rock. So I beg you, it's not every time that you see a rock ending with stone, then you say, oh, once the rock ends with stone, it's a sedimentary. I beg you, they are all not sedimentary rocks. What you used to know which of them is a sedimentary rock is the sediment that it is made up of. The sediment that is made up of. A sand is a sediment, a gravel is a sediment, clay is a sediment, silt is a sediment, mud could be referred to as what? A sediment. So if these ones end with stone, then you can say they are what? Sedimentary rocks. Usually the gravels make up either a conglomerate or breccia. So those ones don't end with what? Stone. Okay, so please let's take note. Sedimentary rock is formed in layers. Usually formed in layers. Sedimentary rocks make up less than 5% of the Earth's crust. They are not really much as compared to the igneous and metamorphic. So these are some examples of rocks. So as I mentioned, limestone is a sedimentary rock, sandstone sedimentary rock, shale is a sedimentary rock, conglomerate, this guy and this guy, they are minerals. Okay, so limestone made up of fine grained calcareous or carbonaceous materials, sandstone made up of sandy materials, shale made up of fine grained materials, which could be silt or clays, okay, very fine grained materials. Conglomerates, as you can see, all these things, these rounded materials in them, we refer to them as what? Pebbles. Okay, so in a conglomerate you can see pebbles, and these are rounded or sub-rounded gravels. Alright, and then they are found within finer grained materials, which are referred to as what? The matrix. Okay, so the matrix is the finer grained materials that are holding the gravels within them, and the whole of this is referred to as what? Conglomerate. If there's a case where the gravels are angular, in this case they are rounded to sub-rounded. If there's a case where they are angular, they are very rough, the corners can be easily seen, we refer to that rock as what? A breccia. BRECCIA. Okay. Metamorphic rocks. So I had already explained them. I'll not take much time. A metamorphic rock forms when any pre-existing rock is altered by heating and increased pressure or tectonic deformation. When a rock is buried, its temperature and pressure increase, causing changes in both the minerals and texture of the rock. These changes are called metamorphism. And the rock formed by these processes is a metamorphic rock because it has gone through what? Metamorphism. What are the things we refer to as what? Metamorphism? The heating, the higher temperature, the higher pressure, and sometimes the tectonic deformation. Those are the things that the rock would have gone through to generate a new rock or a different rock known as what? A metamorphic rock. And the process is what? Metamorphism. Metamorphism also occurs when magma hits nearby rock or when tectonic forces deform rocks. Typical examples of metamorphic rocks are what? Schist, gneiss, and marble. Schist, gneiss, and marble. We also have quartzite, phyllite, and other metamorphic rocks. Okay, so this is how we can picture metamorphism. So over here you'll see an existing igneous rock. How are igneous rocks formed? Oh, okay, we have not yet reached there, so let's rather focus on the ones we've talked about. Sedimentary rocks. Okay, so these rocks that have been formed as a result of weathering, erosion, transportation, deposition, sedimentation, they now get buried and buried and buried. Then they get to what? Get to the compaction stage, and they are cemented, and they now form a sedimentary rock. So maybe at this stage we have the sedimentary rock. If this sedimentary rock continues to find its way downward, going deeper into the earth's crust, then it will start to be impacted by what? Higher temperatures and pressures. And this is what would result in the metamorphism, okay, and it would result, or it would cause a metamorphic rock to be formed. Now let's talk about igneous rocks. How are igneous rocks formed? So I earlier mentioned that we have the magma chamber or the mantle, where magma or molten rock is found. Okay, on the crust, we haven't yet done it, but then I think, yeah, I illustrated where the crust is. That is the top surface where the crust. Yes, I did this. Then we have the mantle, and I mentioned that the mantle is where the magma is. And what is the magma? Magma is molten rock. What is molten rock? Rock is usually supposed to be in the solid state, right? But then when the rock goes through a high level of temperature, it can no more exist in the solid state, so it becomes what? A fluid. Alright, so this fluid, or this rock, solid rock that has now changed into the fluid state, we refer to that fluid state of the rock as what? A molten rock. And then an easier way of naming that is what? Magma. Alright, so this molten rock or this magma, when it is within the subsurface, this is where the pressure is very high. Alright, so when it tries to, or when it gets a slight chance, it will quickly pass through it and come out. Just imagine a classroom that is meant for 50 students, and there are 200 students in that classroom. Because there's no much space for everyone to sit down, everyone is trying to just hang around somewhere. The pressure in that room is very high. Everyone is looking for the easy way out. So immediately the lecturer says, "We are done for today. Come and see speed." He's looking for the next door. He's looking for where to come out. So the pressure is high. So once it finds an easy access, a small route outside, it will quickly what? Pass there and get out, because the pressure is high. So magma has high pressure, okay, because it is found at the lower portions of the subsurface. And so once there is some form of cracks or discontinuities or openings or weak zones within the rock, it will quickly what? Find its way there and pass through it. So when the magma is passing through that weak zone, and then it gets stuck within the subsurface, it is no more in the mantle. It has now moved into the crust, all of this side where there is solid stable rock. We refer to it as what? The crust. When it moves from the mantle and gets into the crust, and because the higher you go, the cooler you become. Initially it was hotter here, but then it will now come up here, and then the temperature is relatively cooler than when it was at the bottom. So because it is cooler here, it will do what? It will solidify, and that takes a very long time. Alright, but eventually it will cool down and it will solidify, because it is no more at a very high temperature. It is at a region where, or at a zone where the temperature is cool enough for it to solidify. When this magma, which was initially fluid or liquid, solidifies, we now refer to it as what? An igneous rock. Alright, now there are two forms of igneous rocks. There are the types that crystallize or solidify within the subsurface, or within the earth, or within the crust. There's another group that continues to find its way and gets to the surface. Once it gets to the surface, we refer to it as what? A volcanic rock. All right, the process of it getting to the surface is initially referred to as a volcano, but then when that magma finds its way to the surface, we will now refer to it as what? Lava. The name will change automatically, just like you have given birth. You have push, and you have pushed the child and he has come out. Once he has come out, you have given birth. The name of the magma will change to lava, and it is this lava that will flow on the ground surface, and while it's flowing, it will get to a point that it would eventually what? Solidify or crystallize. Once it crystallizes, it will also what? Form an igneous rock. So this guy has come to the surface, it has extruded the rocks, it has extruded, it has gotten to the surface. So we say extruded, it has gotten to the surface. So we refer to this type of igneous rocks that occur on the surface as extrusive igneous rock. They have been exposed to the atmosphere, they have extruded and gotten to the surface. So extrusive igneous rocks. Then these guys that formed within the crust and couldn't find their way onto the surface, over here we refer to them as what? Intrusive igneous rock. They have intruded the rock, but then they couldn't find their way to the surface. So intrusive igneous rocks. Okay, so and then there is another aliases to them, or also known as the intrusive igneous rocks can also be called plutonic igneous rocks or plutonic rocks. Then the extrusive igneous rocks can also be referred to as what? Volcanic rocks, because they are the ones that have formed as a result of what? Volcanic activities. So we have two groups of igneous rocks: extrusive and intrusive, or volcanic and plutonic. And these are all formed from what? Magma. When magma, which is in the molten state or in the fluid state, goes through or passes through weak zones and then solidifies along the line, whether inside the earth or outside. Once it solidifies or crystallizes, we refer to that type of rock as what? Igneous rock. Now, between the extrusive and intrusive igneous rocks, which ones do you think would have fine grains? Like this, the material, the mineral grains in it to be very fine. Like when we say fine, we say it is like small, fine grains, small. Let me see if I can. So small particles, fine grain. Then another one being big. The mineral grains are bigger. We are seeing that between the intrusive igneous rocks and then the extrusive igneous rocks, one of them has bigger grained minerals. One of the rocks have bigger grained minerals, and then the other one has smaller grained minerals. Which of them do you think would have the bigger grain and then the smaller grain? So this is smaller grain. We refer to it as fine grain. These are the bigger grain. We refer to it as coarse grain. Now, between the intrusive and extrusive, we say that the extrusive igneous rocks have the finer grains. They have the smaller mineral grains. You can barely even see that this is a mineral grain. Then the intrusive ones, they have what? The coarser grains, or the bigger crystals that you can see. Why is that? When the magma is in the mantle or in the magma chamber. It is in the molten state. It is in the liquid or fluid state, right? Now this guy does and gets to the surface of the earth. Between this surface of the earth and another magma that tries to crystallize within the surface of the earth, between the one on the surface and the one inside, which of them do you think would have a lower temperature? Between this area here and this area, my distance is not sure, my laser is not sure. Between this area here and then this area here, which one do you think will have a lower temperature? Which of them will be colder? It is the one on top, right? Because it is exposed to the atmosphere. So it is certainly going to be colder or having a lower temperature than the guy inside here. Now, if we are saying this one has a lower temperature than this, then between this environment, which is on the surface, and this environment, which is within the subsurface but in the crust, which one do you think would make the molten rock to cool faster? It will be the one on the surface, right? Because this guy is colder here, but this guy is relatively warm. Between this guy outside and this guy inside, this guy is relatively cold. So because the temperature is colder here, the lava that is outside will cool down at a faster rate than this guy that is inside. And because this is cooling down at a faster rate, the mineral grains will not have enough time to crystallize and form their nice crystals that are coarse. Usually they are supposed to look coarse or rough or large grained. Alright? And that's what happens to the ones within the subsurface or in the crust, because they will take a little longer time to crystallize. The mineral grains will be well formed. You will see them clearly. Alright? You can see the coarse grains or the larger grains. You see the felsic and the mafic, the white colored ones, the dark colored ones. You see them nice. Some of them are angular, some of them are having different forms of distribution. You see the mineral grains clearly for the intrusive ones. Alright, because they take a longer time to crystallize. The minerals take a longer time to crystallize. Why? Because the temperature here, even though it's cooler than the mantle area, is still relatively not very cold. Alright, but then the guy over here at the exterior part is very cold, and so it will take it a relatively short period to cool. And because it is just having a very short period to cool, the mineral grains will not have sufficient time to form their nice crystals. So once they are in that molten state, in that mixed up state, they will just quickly crystallize together, and then they are looking small because they didn't have enough time to crystallize out nicely into the various coarse grained mineral grains. I hope it's clear. So we are seeing that there are two types of igneous rocks: the extrusive igneous rocks, which forms when magma erupts and solidifies on the Earth's surface. Because extrusive rocks are so commonly associated with volcanoes, they are also called volcanic rocks. An intrusive igneous rock forms when magma solidifies within the crust. Intrusive rocks are sometimes called plutonic rocks. Then we are saying magma can either rise all the way through the crust to erupt onto the Earth's surface, or it can solidify within the crust. So the one that solidifies within the crust is referred to as intrusive igneous rocks. The one that erupts through the crust onto the earth's surface is referred to as what? Extrusive or volcanic rocks. Lava is fluid magma that flows on the earth's surface. So when magma is within the earth's surface, we still refer to it as magma. Or when there's molten rock within the earth's surface, we refer to it as magma. When that molten rock comes to the surface, we change the name to what? Lava. So, as I mentioned, that one type or one group of the rocks, of the igneous rocks, has rough texture or coarse grains, that you can see the mineral grains way clearly. The other group, you see, these are very fine, small, but you can barely say that this is this mineral, this is this mineral, this is this mineral, right? Because they are all very fine grain. So between this rock and this rock, which one do you think is intrusive and which one do you think is extrusive? Between granite, which is coarse grains, you can see the dark colored minerals, you can see the light colored minerals in them, very coarse grain, very clear. Then rhyolite, where you can see virtually everything looking just like a light colored thing, but then you can't really pinpoint which mineral in particular is. Which one do you think is volcanic or extrusive, and which one do you think is intrusive or plutonic? I'm hoping most of you are right. So this is a volcanic rock. Why? Because it found its way towards the surface, and because it found its way towards the surface, it didn't get a long time to cool. It cooled at a very fast rate, and because it cooled at a very fast rate, the mineral grains quickly solidified together without having time to crystallize out. Okay, but then this guy is what? An intrusive igneous rock. It was formed or it solidified within the earth's crust, and because the temperature there is not as cold as on the earth's surface, it had more time, it had enough time to crystallize the mineral grains out. So although granite and rhyolite contain the same minerals, they have different textures, very different textures, because granite cools slowly and rhyolite cools rapidly. Okay, rhyolite cools rapidly because it was formed on the surface of the earth where the temperature is what? Very low. Granite cools slowly because it was formed within the surface of the earth where the temperature is not as low as the one on the surface. Therefore, the mineral grains are what? Coarse, and then the mineral grains in the rhyolite are what? Fine. So this is another depiction. So all the rocks formed within, the igneous rocks formed within the subsurface are what? Intrusive igneous rocks, and then the ones that find their way onto the surface are what? The extrusive igneous rocks. So this guy here, you see the way it's very fine. Okay, it's referred to as what? An extrusive igneous rock, obsidian. Then we have another one here. You see, is it coarse grain or it's fine grain? You can barely see the mineral grains. You can barely see them. Okay, so this one is what? Basalt. Basalt because it is dark colored, alright, and it is fine grained igneous rock. It is an extrusive igneous rock. Pumice. Pumice is a specialized guy. You can, all these things you are seeing in them, like the dark, they are not minerals. These are holes or vesicles, or these are vesicles within the rock, and they are formed as a result of the gases that were caught up during the volcanic eruption, alright, that eventually bubbled out. leaving behind some of these pores or these vesicles. So we see this guy here, granite. Once again, it is an example of what? Intrusive igneous rock, because you can see the mineral grains, alright, and it took a long time for it to crystallize because it was found within the subsurface. Okay, we are approaching the end. So we talked about metamorphic rocks. So these are some of the examples. A gneiss, okay, the realignment of the mineral grains. So we mentioned that because of temperature, because of pressure, there will be realignment or reformation of some minerals. And in the case of gneiss, you see that there is a color banding. Dark minerals form a line, light colored minerals form a line, dark minerals form a line. So that is one thing that depicts a gneiss. Okay, so when you hear gneiss, metamorphic rock with dark and light colored minerals alternating. Marble is another example of a metamorphic rock. You see that in this case there are no alignment of the mineral grains. Alright, this marble is formed from limestone. Okay, marble is formed from limestone. Limestone is a sedimentary rock. Marble is the metamorphic version when it undergoes intensive temperature. Okay, then schist is also another metamorphic rock. You can see some form of realignment of the mineral grains in them. Okay, and then we also have slate, another metamorphic igneous rock. They come in the form of how do I mention it, like sheets. Okay, like you can take this part, peel it off, take this one, peel it off, take this, peel it off. So they are in the form of a slate, just like the slate you were using to write ABCD back in the days. Okay, the final slide talks about the rock cycle. So the rock cycle talks about how a particular rock type can be transformed into another rock type. Alright, so how can an igneous rock be transformed into a sedimentary rock? When it undergoes weathering, we've talked about all this: weathering, erosion, then it forms sediment. These sediments are now deposited, they are buried, they are compacted, they are cemented, then they form a sedimentary rock. How can a sedimentary rock become a metamorphic rock? When this sedimentary rock is buried at a deeper depth and undergoes heat and pressure, then that process is what? Metamorphism. Then the metamorphism of the sedimentary rock will now result in what? A metamorphic rock. How can a metamorphic rock become a sedimentary rock? When this metamorphic rock goes through what? Weathering and erosion, becomes a sediment, and then goes through these processes to become a sedimentary rock. How can a metamorphic rock become an igneous rock? When this metamorphic rock continues to undergo intensive heat to the point where it melts. Alright, it will have to melt because remember how we say an igneous rock is formed. An igneous rock is formed when a molten rock or the magma solidifies, then it forms an igneous rock. So it means it has to be in the molten state, or it has to be in the fluid state before it will solidify to form an igneous rock. So when this metamorphic rock continues to undergo higher temperatures and it melts and it forms lava or magma and solidifies, then it would form an igneous rock. How will a sedimentary rock form an igneous rock? When this sedimentary rock undergoes what? Intensive temperature and it melts, then it forms magma or lava, solidifies, and becomes an igneous rock. How can an igneous rock become a metamorphic rock? When this igneous rock goes through what? Intensive heat and pressure and metamorphosis and becomes a metamorphic rock. So all these three rock types can be converted or transformed into each other, and the process of these rock types transforming or getting converted into another rock type is referred to as what? The rock cycle. The rock cycle. Okay, I hope this is clear enough. Ladies and gentlemen, we've come to the end of the first lecture.